Hey guys, today we will be learning about a key mechanism seen in many organic chemistry reactions called nucleophilic acyl substitution, or NAS. So, we will be going over the general mechanism of NAS and how this mechanism plays out with different reaction conditions. The three conditions we will be going over are neutral, basic, and acidic. So, similar to an SN1 or SN2 reaction, NAS results in the substitution of a leaving group with the nucleophile. But however, NAS is seen with different starting reagents, primarily carboxylic acid derivatives. So now let's go over the general mechanism. So first we start with our carboxylic acid derivative right here, and then we're going to attack it with a nucleophile. This will then produce a group where the nucleophile has replaced the leaving group and then the leaving group here. Okay, so now we are going to start breaking it down with our first reaction condition, which is a neutral reaction condition.
So the neutral condition can only be seen with acyl chlorides and anhydrides. And this basically is when a protonated nucleophile comes and attacks the already in existence carboxylic acid derivative. So based on this general mechanism, you can see that the nucleophile comes and attacks the carbonyl carbon, which pushes up the oxygen or the electrons onto the oxygen, resulting in an sp3 hybridized molecule, which then gets the reformation of the double bond on the oxygen, pushing off the leaving group, resulting in this final product, which can be seen right here. So now we'll go over a specific example of that, of when this reaction actually takes place in chemistry and how to do this mechanism. So we're going to start with an acyl chloride for this, which is one of the two ways that the neutral conditions can be applied. So first you start with the carboxylic acid derivative. In this case, it's an acyl chloride, and you come in with a nucleophile, and in this case, we're going to use water. So you have the water molecule, and it begins when the water molecule's electrons on the oxygen come in and attack the carbonyl carbon right at the base, pushing off the double bond electrons onto the oxygen. So this results in an sp3 carbonized molecule with a negative oxygen, the chlorine, and the water with a positive charge. Next, the excess electrons from the oxygen come back, reform the double bond, which push off this chlorine group, resulting in the formation of this new molecule with a double bond connected to the water molecule. Double bond carbonyl group. Finally, the chlorine, which was just pushed off, comes and deprotonates the water molecule, resulting in your final product, which is a carboxylic acid and hydrochloric acid.
So next we will be going over another reaction condition, in this case a basic reaction condition. Mostly all the carboxylic acid derivatives can be applied using a base catalyst, esters, amides, nitriles, all of that. So as you can see, the nucleophile in this case is not protonated, and it will directly attack the carbonyl C, and then the double bond will reform, kicking out the leaving group. So let's look at a more specific example using an ester. So here we have our nucleophile. It will come from NaOH since this is a basic reaction. So here we will have our OH group. And then this will attack the carbonyl C. Pushing up electrons there, creating a negative charge on the O, and an sp3 hybridized molecule. Then the double bond will reform, and the leaving group will leave, forming a carboxylic acid. Now, there we have our final molecule, and then that ester over there.
And finally, we're going to cover the third condition seen with the NAS mechanism, which is found under acidic conditions. So this is the most common type of NAS conditions you'll be seeing, and it's really important that you understand this to fully comprehend how this mechanism takes place. So as you can see from the general reaction, unlike the other two mechanisms, this begins with the pronation of the oxygen group. After the oxygen group is pronated, the nucleophile comes and attacks the carbonyl carbon, which results in the sp3 carbonized molecule, with the leaving group nucleophile and oxygen still in place. After this, the leaving group deprotonates the nucleophile, forming a positive charge leaving group and a neutral nucleophile. Then, the double bond of the oxygen is reformed, kicking off the leaving group, which results in a protonated oxygen double bond connected to the original R group and the newly added nucleophile. Finally, the conjugate base comes in and deprotonates the oxygen, resulting in your final product, which can be found as the newly formed carboxylic acid derivative and the protonated leaving group. So now we're going to show you a more specific example of when you might see this with anhydride. So this begins with the anhydride molecule. So we'll start with that molecule. As you can see, it is connected by an O bond, and you start with the protonation of one of the oxygen molecules that are double bond to the carbon. It doesn't matter which one for this instance, since the molecule is identical on either side. So we'll just start over here, and these come out and attack that hydrogen molecule. So at this point, we have formed the anhydride, with one half of it being identical to the previous molecule, and the other half being a protonated hydrogen double bond that is positively charged. Next, the water molecule that we're using as the nucleophile will come in and attack the carbonyl carbon directly on, pushing off the electrons back onto the oxygen. So this will result with the sp3 hybridized carbon, the oxygen group, or the water group, a hydroxide group, and the other half of the anhydride. At this point, this middle oxygen will come and deprotonate the newly added water group, pushing those electrons back onto that oxygen. This will result in the formation of this molecule here. With two hydroxyl groups on it. Now, the double bond will reform on the carbonyl carbon, pushing off this half of the anhydride that has been newly protonated, which will result in a carboxylic acid with a protonated oxygen that is double bound to the carbon compound. Finally, the conjugate base, which in this case would be an OH, since the original nucleophile was water, will come in and deprotonate that oxygen, pushing those electrons back onto that bond, resulting in your final product, which is simply a carboxylic acid. And this will be left with the carboxylic acid that is formed from this process along with it. So in this scenario, you end with two carboxylic acids. One really important piece of the acidic conditions is that the entire mechanism is reversible, which means when water is applied, every step can be reduced back to its previous molecule. It's also important to note that this reaction for acidic conditions is the same as the Pfister acidification, which is another important piece in organic chemistry reactions.
And that is all. We have covered the basics of nucleophilic acyl substitution and their 3 conditions. We hope you enjoyed watching our video and learned this very important mechanism.
And please remember, as you go through your chemistry career, to support the Richmond Black Widows as they continue to dominate the Richmond football scene.